Welcome to the lesson on the types of electric motors used in battery electric vehicles. By the end of this lesson, you will be able to identify and compare various types of electric motors, with a specific focus on those used in battery electric vehicles. You'll gain the ability to describe these motor types and contrast them based on key factors such as efficiency, cost, complexity, and typical applications. Finally, you will recognize the performance characteristics of electric motors in BEVs, including their instant torque, smooth acceleration, and regenerative braking capabilities. Electric motors can be broadly categorized into two main types, DC motors and AC motors. DC motors include brushless DC motors, abbreviated as BLDC, and brushed DC motors, which are less common in modern BEVs. AC motors include synchronous motors, particularly permanent magnet synchronous motors, abbreviated as PMSM, that are widely used in BEVs. Asynchronous motors, also known as induction motors, are another common choice for BEVs. Other types of electric motors, such as switched reluctance motors, servo motors, and stepper motors, are less frequently used in BEVs for propulsion. In summary, the two most common types of motors used in BEV propulsion are permanent magnet synchronous motors and induction motors. These motors offer high efficiency, reliability, and performance, making them suitable for electric vehicle applications. Before we discuss the specifics of each type of motor, let us take a look at the main differences between different motor categories, beginning with the comparison of brushed and brushless DC motors. Brushed and brushless DC motors differ in their commutation methods, maintenance requirements, efficiency, and speed control. Brushed DC motors use mechanical commutation with brushes and a commutator, requiring regular maintenance due to brush wear and resulting in lower efficiency due to brush friction. They offer simple speed control. In contrast, brushless DC motors employ electronic commutation using sensors or sensorless control, eliminating the need for brushes and providing low maintenance. BLDCs have higher efficiency due to the absence of brush friction losses and offer precise speed control using electronic controllers. Brushed and brushless DC motors also differ in terms of power density, cost, noise, and electromagnetic interference in typical applications. Brushed DC motors have lower power density and lower cost due to their simple construction. They generate higher noise and electromagnetic interference. Brushed DC motors are commonly used in low-cost and low-power applications. In contrast, brushless DC motors have higher power density and higher cost due to the complex electronics and magnets used in their construction. BLDCs produce lower noise and reduced electromagnetic interference. They are typically used in high-efficiency and high-performance applications. Now let us look at some of the main differences between the two types of AC motors, namely synchronous and asynchronous AC motors. Synchronous motors operate at a constant speed, synchronized with the frequency of the power supply, while asynchronous motors have speeds that vary with load and are always less than the synchronous speed. The rotor of a synchronous motor is constructed using permanent magnets or electromagnets with DC excitation, whereas asynchronous motors have rotors with conductors or bars arranged in a squirrel cage or wound rotor configuration. Synchronous motors require an additional mechanism, such as a variable frequency drive or an auxiliary motor, to start and bring the rotor up to synchronous speed. In contrast, asynchronous motors can start directly when connected to the power supply. Synchronous motors are more efficient, especially at full load, and provide constant torque at synchronous speed. In contrast, asynchronous motors are less efficient, particularly at partial loads. Synchronous motors provide constant torque at synchronous speed. They are used in high-precision applications that require constant speed, such as generators, compressors, and mills. However, synchronous motors are more expensive due to their complex rotor construction and additional starting mechanisms. On the other hand, the torque of asynchronous motors varies with speed and load. They are commonly used in general-purpose applications with variable loads, such as pumps, fans, and conveyor belts. Asynchronous motors are less expensive and simpler in construction compared to synchronous motors. Let us now focus on the two main types of motors used in BEVs: permanent magnet synchronous motor and induction motor. A permanent magnet synchronous motor, abbreviated as PMSM, is a type of AC synchronous motor that combines features of both brushless DC motors and induction motors. The rotor of a PMSM contains permanent magnets, while the stator is equipped with windings that are energized with alternating current. When the AC supply is applied to the stator windings, it creates a rotating magnetic field, causing the rotor to spin at a synchronous speed determined by the frequency of the AC supply. This unique combination of permanent magnets and AC-energized stator windings allows PMSMs to achieve precise speed control and high efficiency in various applications. Permanent magnet synchronous motors offer several advantages, including high power density, efficiency, and a wide constant power speed range. They can deliver high torque even at low speeds and have a compact size, making them suitable for various applications. However, PMSMs also have some disadvantages, such as high cost compared to other motor types, potential issues with magnet demagnetization, and the requirement for complex control algorithms to operate effectively. Despite these drawbacks, PMSMs are the most commonly used motor type in battery electric vehicles, with notable examples including the Chevrolet Bolt EV, BMW i3, Ford Focus Electric, and Nissan Leaf. An induction motor, abbreviated as IM, also known as a squirrel cage motor, is an AC asynchronous motor that relies on electromagnetic induction to generate torque. The stator creates a rotating magnetic field, which induces currents in the rotor's conductive bars, producing a twisting torque. The rotor speed is slightly lower than the speed of the rotating magnetic field, resulting in an asynchronous operation. Induction motors are known for their reliability, robustness, and simple construction, making them a popular choice in various industrial applications. The rotor consists of a series of conductive bars, which are typically arranged in a squirrel cage configuration, hence the alternative name for this type of motor. Induction motors offer several advantages, including low cost and maintenance, mature technology, well-established manufacturing processes, long life, and a wide speed range. These factors make them an attractive option for various applications. However, IMs have some disadvantages compared to PMSMs, such as slightly lower efficiency, limited low-speed torque, and a decrease in speed with increasing load. Despite these limitations, induction motors are the preferred choice for performance-oriented battery electric vehicles, with notable examples including the Tesla Model S, Tesla Model X, Toyota RAV4 EV, and the iconic GM EV1. Let us now compare the two main types of motors used in BEVs. PMSMs offer the highest efficiency among the motor types, typically ranging from 90 to 95%. However, they also come with the highest cost due to the use of permanent magnets in their construction. PMSMs have moderate complexity, as they require precise control to operate effectively. Induction motors, on the other hand, have moderate efficiency, typically ranging from 80 to 90%. They have the lowest cost among the two motor types due to their simple rotor construction and rugged design. IMs also have low complexity, making them easy to manufacture and maintain. PMSMs offer high power density as compared to induction motors. PMSMs offer precise speed control over a wide range. They have moderate overload capacity and are commonly used in applications that require high performance, such as electric vehicles, robotics, and industrial automation. Induction motors have moderate speed control capabilities. However, they excel in terms of overload capacity, making them suitable for applications that require high torque and robustness. IMs are widely used in general-purpose industrial applications, such as pumps, fans, and compressors, where their simple construction and reliability are advantageous. They are also a good choice for battery electric vehicles. Let us now discuss some of the main performance characteristics that make electric motors highly suitable for BEV applications. The characteristics include torque and power, speed range, reliability and maintenance, noise and vibration, thermal management, and overload capability. Electric motors in BEVs offer several key performance advantages. They provide high torque from zero speed, enabling quick acceleration and responsive performance. The torque output remains constant over a wide speed range, ensuring smooth and consistent power delivery. The high torque density of electric motors allows for compact and lightweight designs, contributing to overall vehicle efficiency. Electric motors also have a high power-to-weight ratio and can achieve peak power quickly. The power output can be easily scaled by selecting appropriate motor sizes or using multiple motors, allowing manufacturers to design BEVs with varying performance requirements. Electric motors and battery electric vehicles offer a wide speed range, allowing for efficient operation from 0 to high speeds. This eliminates the need for complex multi-speed transmissions found in internal combustion engine vehicles. Power electronics and advanced control algorithms work together to regulate the power supplied to the electric motor, enabling precise speed control and optimizing overall efficiency. Permanent magnet synchronous motors are particularly well suited for BEVs as they offer a wide, constant power speed range, ensuring consistent performance at higher speeds without sacrificing efficiency or power output. These characteristics enable BEVs to deliver smooth, responsive, and efficient performance across a wide range of driving conditions. With fewer moving parts, electric motors have lower maintenance requirements and higher reliability due to their simple construction. This translates to reduced maintenance costs and increased vehicle uptime for BEV owners. Additionally, due to the simpler construction, electric motors generate significantly lower noise and vibration levels compared to internal combustion engines. Thermal management and overload capability are important performance characteristics of electric motors and battery electric vehicles. During operation, electric motors generate heat, which requires effective dissipation to maintain optimal performance and prevent damage. Battery vehicles often employ liquid cooling systems to manage motor temperatures effectively. Induction motors used in some BEVs have a high overload capability, allowing them to handle short periods of increased torque demand without sustaining damage. This is particularly useful in situations such as overtaking, climbing steep inclines, or other scenarios that require a temporary boost in power output. Proper thermal management and the ability to handle overload conditions ensure that electric motors and BEVs can deliver consistent performance and reliability across a wide range of driving situations. We have now reached the end of the lesson, and let us summarize what we have learned. The most common types of electric motors used in battery electric vehicles are permanent magnet synchronous motors and induction motors. PMSMs offer high efficiency, power density, and precise speed control, but come with higher costs. IMs, on the other hand, are lower in cost and complexity, robust, and preferred for performance-oriented BEVs. Electric motors offer several performance benefits, including instant torque, a wide speed range, high reliability, low noise, and the ability to handle power demands and overloads with ease. Thank you.